Okay. So let's look at that PDF some more. This principal fault rupture location uncertainty. As we saw from Peterson et al., they made a very good start at this. Rui Chen and Mark Peterson have continued this work, probably Tim with your help. And what we're trying to do with this exercise is we're trying to come up with the location uncertainty. What is the difference between the rupture trace, where we observe it to occur after the rupture happens, and that's expressed by the squiggly straight line, and we want to compare that to some estimate of where we expected that rupture to occur from the mapping of our active fault. And we know from doing field camp and other exercises that it's not always easy, and it's not always on the same basis that we map a fault trace. We have accurately located fault traces, approximately located fault traces. Sometimes those faults we draw as being concealed beneath younger alluvium or artificial fill. And this pattern over here is supposed to express an inferred map trace. We really don't have a lot of confidence that it's going through here, but boy, we think the fault trace should go through here. And what Peterson did is they looked at the very few examples they had, and they came up with a set of measurements of the distance between the rupture that actually occurred and the previously mapped fault trace. And they divided their measurements based on mapping accuracy designations that occurred beforehand. And they found, fortunately, that for traces that were accurately mapped, they tended to be closer to the eventual rupture. So the mean difference in distance was a lot smaller. And with this decreasing confidence in the map location, they were able to show that there was an increase in that mean estimate. So less confident, that correlates with a greater difference between where the mapping, where the rupture occurred versus where we expected it to occur. So in addition to this basic result, they found also that it made a huge difference where you are along a rupture. And this is a picture of the Hector Mine rupture. This is an enlargement at the same scale of two different reaches. One where we have a relatively simple reach, and one where we have this great structural complexity. And they were able to show that indeed in areas of structural complexity, there was much larger uncertainties in our location of, from pre-rupture mapping to the actual earthquake. There were much greater uncertainties of where that was going to be compared to areas of relatively simple geometries and simple rupture patterns. So I'm going to turn now. These are the slides that Chris shared with us on Tuesday. And this is an important example that underscores why we have this class and why we're really motivated on the hazard side to have the students go through this exercise. This is an example from the Ridgecrest earthquake area, and this was the fault mapping from Q faults. So this was the starting point mapping of a publicly statewide available data set. And so if we were going to do the same exercise that Peterson et al. Did of comparing the Ridgecrest earthquake rupture to this pre-rupture mapping, we wouldn't really be looking at uncertainties, I would argue. We're really looking at something that's related to an error. This is not a well-posed hypothesis of really where we expect the rupture to occur. Instead, this is a compromise based on a compilation scale and just a resolution of the mapping. And if anyone were even to suggest putting this trace on here with this simple linear location, I think at very minimum, they would say, no, we really intend it to run right along this geomorphic low set of ridges. So if we're comparing the rupture to this, we're introducing error, not really examining uncertainty. Okay, this represents a much, much better starting point for our analysis. This is something that is a very considerate, deliberate attempt by qualified, educated geologists and mappers who are trying to look at different characteristics of the landscape and infer where faulting has occurred recently in the past. This is a much better starting point, and importantly, for the hazard projects we do in practice, we're typically trying to create these maps as part of our phases of investigation. And so what we want from the students, from you students, is to be able to generate maps like this in areas that will give us much more robust comparisons to say, when we add the earthquake rupture to it, now we're really going to make some interesting comparisons in fault location uncertainty. So the traces that we can map with various degrees of confidence before, we can compare those to where the ruptures occur. Let's see. Okay, I'm dreadfully short on time, so I'm going to, let's see. Okay, very quickly, we're going to shift to how we look at distributed displacement hazard. So we've been looking at some of the Peterson et al. Equations for principal displacement with a capital D. Now, one of the other formulations they have is to how to look at the conditional probability of displacement when we're explicitly looking at a location that's away from the principal fault. And this conditional probability is, what is the likelihood, what is the conditional probability that we'll get non-zero displacement at our site, again, given the distance from the trace, given the site, the cell dimension size, Z, and given that this earthquake produces surface rupture at all. The approach that Peterson et al. Used was to take advantage of Tim Dawson and to force him to go into a GIS dark room and come up with a grid system where for various grid cell dimension sizes, from 25 meters up to 200 meters, he would impose a grid system similar to this, and he would count at different cell dimensions or different cell lengths away from the principal rupture how often cells contained an example of a secondary or distributed displacement. And so for the straight reach, you can see that even at a 50-meter cell size, it's incredibly rare for this reach that we have a secondary displacement at a given distance, even 50 meters away from our principal rupture zone. Whereas in this area of complexity, you can see, in contrast, it's quite common at significant distance away from where the principal trace would be going through. It's quite common to get encounters with secondary ruptures. And so we know that structural complexity, at least in this example, is a really important driver over what this conditional probability would be. Unfortunately, in the Peterson et al. Models, they weren't able to incorporate the structural complexity into the model. This is showing an example of the effect of using different cell sizes. And so first we looked at something that was about 50 meters. This is about 200 meters. And you can see again, when we're at a 200-meter distance, even in these very large cell sizes, structurally simple area, the probability that we're going to get distributed displacement out here in this reach is essentially zero. But over here in this structurally complicated area, we have much greater probabilities. A much higher percent of the grid cells 200 meters away from the principal source have some expression of distributed displacement. So you see in the Peterson et al. Paper, they show the results of this exercise that Tim went through different ways. They give tabulated data showing how you can use the equations they provide to come up with quantitative estimates of the probabilities, and they report standard deviations, thankfully. And graphically, they also show the results. And these graphical results, to me, are the biggest motivation for the exercise that you guys are going through, because this is their preferred model, where we have the rupture probability given a cell size with distance away from the rupture. And you can see that when our model gets to be about a 1% probability that we're going to get rupture, a distributed rupture 2 kilometers away, this is their preferred model, but the uncertainty is enormous. For this earthquake up here, we're getting closer to 8 or 10% probability in a cell. For this spot down here, we're getting closer to a 1 in 1,000 chance, a 0.1% probability that we're going to get rupture in this cell. For our hazard curve, this really shifts that hazard curve way up and down and can completely make the difference between a client saying that they're going to mitigate by just not doing anything. They're going to accept the risk, all the way to taking it very seriously and saying that they're going to mitigate by employing a very expensive design, perhaps. One of the other things that's really alarming about these data and the spread, almost all of these points up here are from the Landers earthquake. Almost all of these points down here are from one of the Turkey earthquakes that occurred in 1999. And in between, these dots aren't randomly scattered, but you can almost see a different profile line, one different profile line for each of the few earthquakes that they studied. And what that tells us is it tells us that the average model is really specific. It's not really an average condition that you would expect for any one given fault. So when you're doing one of these hazard studies, you're constantly having to ask yourself, is this study area, is this fault I'm examining, is it an average type fault? Is it more of a Landers type environment? Is it more of a Turkey, North Anatolian fault type environment? And even given a complex rupture like Hector Mine, am I in this type of environment, or am I in this more complex type of environment? And the way we're going to get there is through this class and through the exercises that we're doing. And so again, if this is an example of the type of outcome of geomorphic, pre-rupture mapping, and again, this is the type of information we try to collect as consultants before these ruptures happen. So given that we have this set of black lines, and then given that this rupture occurs, we hopefully after the class and after several years of this class, we'll be able to constantly regrid and re-update these relationships, and we'll be able to make much more useful tests. So we'll be able to test, how does my conditional probability change given that someone identified a tectonic geomorphic feature in that cell? Does that increase the likelihood that rupture is actually going to be in here? Is it going to have no consequence on whether rupture is going to be here? So basically pre-rupture mapping, we'll see doesn't have any predictive value of where rupture is going to occur, or otherwise. Okay, so I am out of time. I have 2 summary slides that go through some of the main points I hope to make during this talk. And these slides will be part of the class notes. You can refer to them as you'd like. But again, the guidance and the hopes here for this class, I'd really love that you all prioritize really high quality mapping work, where we really want to minimize introducing errors in mapping to the analysis. And we really would love to see clear documentation. So we think it's going to be really important, how confident are you in a certain trace that you map through geomorphic expression. And also, it's wonderful if you will clearly document the type of geomorphic expression you see. Because again, we hope that those will have some kind of predictive value to help us improve our models. Also, our hopes for this class is that when you go through these exercise of doing geomorphic mapping, we really want to prioritize individual work rather than group work. We'd love for you guys to get guidance from the instructors, but we're really hoping to get differences in interpretations. We want to really understand how repeatable is the exercise of fault mapping from geomorphology, and how repeatable is that exercise in different types of climatic environments. And then maybe most importantly, the correct answer for your mapping exercise is not what happens in the actual rupture. And so a lot of the exercises that you're going to do towards the end of the class, you are going to be mapping geomorphic expression of faults using imagery prior to actual earthquake ruptures. And there's going to be the temptation to look at what actually happened during that rupture, to look ahead to see what rupture pattern occurred in the end. But that sort of peeking or that sort of cheating really could compromise the whole integrity of the project. Because as consultants, we don't have that opportunity to cheat and really look ahead and see what what rupture happens in the future. Okay, so I'll stop there. Are there any questions from the group?
Yeah, we have a good maybe 5 minutes for questions, so please don't hesitate to ask Steve any questions about what we talked about, or perhaps how we envisioned the project.
I had a quick one about the cell size. So when they choose the range of it, and then when you want to use the regression equation to go at a site, are you expected to like choose the same cell size across the entire one? Because I know like 20 would be some for a simple one, but a more complex one would be a larger Z size. So on that grid, they're using the same, but can you use different cell sizes if you're just trying to do like a more specific area?
Yeah, that's a really good question. The motivation behind different cell sizes is it really in the application of these hazard models to different types of infrastructure. And so if we're looking at doing a hazard analysis for a building, we might be interested in calculating hazard just for that building based on one of these smaller site dimensions. And so it's less a matter of what's a convenient or appropriate grid scale for counting and for, so in other words, the purpose of the different sizes is more on the application at the user end, and it's less a matter of what's the optimal grid size for the input for the mapping part of it. So again, if I'm going to do a study for a small building, I'll look at 50-meter cell dimensions. If I'm examining a water treatment plant that has many different tanks and interconnected pipes and other facilities where the vulnerability of that whole water treatment plant is very interconnected and linked, I'm going to want to calculate my hazard using that much larger cell dimension. Does that make sense?
Yeah. So just it's dependent on what you're trying to get out of the model?
Yes, exactly. It's how we're applying that model to give us hazard assessments for different types and different sizes of infrastructure.
Okay. And then if you were using it on like a larger project, maybe like an oil pipeline, you would have to use the same cell size across the whole area?
Okay, so that's a really excellent question, and it introduces a real big trap. This cell grid approach is wonderful for isolated structures, as large as a nuclear facility, as small as an outhouse. But when we switch and when we're now talking about lifelines, pipelines, or rail corridors or highway corridors. With lifelines, the grid cell approach really runs into problems. And that's something that we may not have time to totally discuss today. But really quickly, if we have a pipeline that's running through here, we know that pipeline somewhere has to cross the primary fault. And we know that that lifeline has a reasonable chance of crossing secondary faults somewhere along it. If we use these grid cells and we try to do one calculation here for this part of the pipe, and then one calculation here for this part of the pipe, a third calculation here for this part of the pipe, one of the things this approach in current models don't do is they don't take into account the correlation, the dependence of hazard in one cell compared to the hazard in the adjacent cell. And so we really, unfortunately, can't use the Peterson et al. Formulation for lifelines. We have to do something more complicated. But so that's a confusing answer to an excellent, insightful question.
Thank you, that was helpful.
Maybe one more question.
So I do have a question. You were saying that looking at the actual ruptures does not help when looking at the mapping exercises that we're going to be doing. So could you maybe explain that a little bit more? Is that because like when you have one rupture, it's not necessarily always in the same place, or I don't know, maybe explain.
Okay, I may, yeah, thanks for that question. I may have gotten ahead of myself a little bit. So in this class, there's, Chris Madugo presented, he highlighted this case and talked about PG&E's infrastructure and what the concerns are on PG&E's end about having a more resilient, safe pipe system and system of dams, et cetera. This class is supposed to really introduce you to hazard in consulting practice and how these different models really help us to characterize fault displacement hazard. The next set of lectures, I believe, you're going to be introduced to various types of earthquake environments, various types of faulting environments, and different types of data and different types of approaches to do geomorphic mapping. And the intent of the geomorphic mapping is you are trying to identify where the major fault traces are in detail, and you're trying to identify where other maybe secondary faults are located. So you're trying to come up with as complete a description as you can of what is the geomorphic expression, what's the recognizable expression of faulting in the landscape. Now, it's a different question of what happens during large earthquakes when they rupture the surface. Some rupture traces won't necessarily leave geomorphic expression. It could be because they're in environments where they'll be actively buried and the signature will be actively erased. It may be because the displacements are very small and so geomorphic processes will remove all manifestation of them. But other traces might leave beautiful and very complete geomorphic records for a very, very long time, particularly if that movement is occurring, it has a sharp differential vertical component to it. If you're juxtaposing different materials of different erodibilities, there are other displacements that can leave an excellent and very long-lasting geomorphic expression. When we as consultants or we as hazard analysts try to characterize rupture hazard, what we have is this geomorphic mapping, and we're very tempted to make a substitution in our minds. We're very tempted to say this pattern of geomorphic mapping is equivalent to fault rupture, and it's not. And so what I was trying to emphasize is in your independent projects, you're going to be assigned faults, reaches of faults that have ruptured historically. Only we don't want you to use the data. We don't want you to use the air photos, the LiDAR images after the rupture occurred to help you in your mapping. We want you to only rely on air photos, topographic data sets, etc., from before the rupture occurred. So that is the experiment that we have to do in consulting, and we have to do in hazard analysis for society. We need to rely on geomorphic expression and geologic mapping as a proxy, as an indicator for how ruptures might occur. And we would like you guys to build a data set of very high quality, very good detailed mapping in areas that have ruptured the surface, so we can then make that comparison. How does a geomorphic map compare to an actual rupture map? One of the things you mentioned is a really important point. What's the variability from one rupture to the next, right? The next ridge crest earthquake, will it produce the same pattern or will it produce a completely different pattern? That's a whole nother level of analysis that is just nearly impossible to make in the geological sciences. And it's an excellent point, but again, the major goal for us is to be able to do that later comparison of the difference between a geomorphic map and a rupture pattern, so that we can incorporate that uncertainty in our models and make better models. Does that help, Sean?
Yeah, thank you, Steve.
Okay.
Appreciate it.
Hi, this is Chris. I also wanted to clarify that this class isn't just a consulting project.
Yes, it is.
It's basically teaching the students how to do geomorphic mapping that you'd use for an academic study to characterize the activity of a fault, to understand the tectonics of a region. Those are the basic skills you're going to be learning. But for those data sets to do the final mapping project on, we've selected data for faults that have ruptured historically to turn this more into a research project that could help consulting studies in the future. So I don't know if it was mentioned in the syllabus, but ultimately the data sets that are generated by this class and other classes that will happen in the future would go into a paper with all the students being a co-author on looking at this uncertainty between geomorphic mapping and where ruptures actually occur.
Thanks, Chris.
Yeah, and this is Rich. I'll just add to that, yeah, we'll be showing examples from around the world in different climatic environments, and showing how places with progressive offsets may leave a good signature in the landscape that may help define a primary trace. And then off the main primary trace, things may be more subtle and less preserved. And then, we'll go over sort of how to qualitatively assess your confidence in different ruptured traces. And so we'll show examples and then kind of teach you how to go through and actually map, make an interpretation of where the primary and secondary traces are and in generating these fault maps.
All right, let's say thank you to Steve for giving us such a nice presentation this morning.
Thanks, Steve.
Hey,
And,
you're welcome.
Speaking about learning about how to generate these faulting maps, Ramon is now going to discuss